Alright everybody, this is going to be fuzzing and exploit development with the Metasploit framework. I am Ellie Kara. Also go by Nullthreat, as we just said. I'm a senior information security analyst with a company down in Bowling Green. This is my standard disclaimer. Do not take anything that I say as fact. I have been wrong before, and I will be wrong again. It might be during this presentation. First things first. You guys are going to need some files if you want to replicate this presentation. This is a very complex topic, and if you've never done this before, I highly recommend you not trying to follow along. Watch the whole thing through to the end. Download these files, all the files that are right here. The password for that is Metasploit. Are all you guys need to replicate this at home. So I'll leave that up for a few minutes, let you guys write that down and or grab the files. Like I said, I would not try to do this as I go along because I do talk kind of fast. And if you get behind it all and you've never done this stuff before, you'll get lost. Because I did, like last week, and I was doing it. So, give you guys a minute there. While it's going on, has anybody ever done exploit development, whether in Metasploit or in any other language, or done fuzzing or anything like that? So 1, 2, a few. Okay. Yeah, Dave.
Did you have that colon there?
Do what? This colon? Yeah, you did that. And the files, when you get it, there'll be 2 Windows files and 2 files for you to load into Metasploit, and I'll go through where those files need to be placed as we go along. There's placed at 2 Ruby files and 2 executables. Has anybody here ever used a debugger other than the guys that have done this kind of stuff? Okay, good. All right, well, everybody get that needed it? Leave it up for a minute. All right, we'll go ahead. All right, so if we're going to talk about buffer overflows, probably should cover what is an overflow. The very generic answer, 10,000 foot view is it's when you put too much stuff in a space that's not designed for that much stuff. There are multiple types of overflows that are exploited. We're focusing on stack-based overflows because they're easy. For a first overflow, this is one of the easiest out there. As I said earlier, this became really popular. Frac49 Alpha 1's article, Smashing the Stack for Fun and Profit. So, what is the stack? The stack is used, it's part of memory used to hold functions, function variables, user inputs, any data the app needs to get to repeat, it stores on the stack. The stack is first in, first out, meaning that when you put whatever goes in, has to come out. So it's like a box. You put a bunch of stuff in it. If you need the thing out of the bottom, you got to take all the stuff off the top to get to the bottom. Here's a picture. So, as you can see here, we have an array of characters, 12 characters, and some other stuff that I'll get into here in a minute. The big thing is, it's waiting for 12 characters. When we put in the word hello with a null terminator, it fits in there just fine. If we send a bunch of A's, for example, you can see we overwrote the other stuff. Now, what is that other stuff? The red one is important, the return address. That's what tells the application what to do. So here you can see we sent a bunch of A's, and now we've put in something down here. It's kind of hard to see, I know. It's an address in memory, which happens to correspond with this address up here. So when this application processes this information, it would then go here and start reading what we've put in. Does that make sense to everybody? I'm going to stop a lot here and ask if anybody's getting lost, because, like I said, if we lose anybody at any point, you're probably going to be lost for the rest of the presentation. Yes?
I have a question, though. Will this documentation and presentation be available?
Yes, it'll be on my website, nullthreat.net. Adrian will have it on his website. I have videos that go along with this, and the presentation, and I'm available for questions. So, yes, this will all be out there. And I'll also have the files that I've referred to there will also be available on the website. Okay, so one way that we find these overflows is through a process called fuzzing. Fuzzing is really neat because all you got to do is send a bunch of crap at a program that it's not expecting and wait for it to crash. And this has become a largely automated process here recently where you can set it up, let it go for days, and come back and find all the crashes. Basically, the whole goal of fuzzing is to make the application cry. And if we can make it cry in the way we want it to, we win. And what we want in this case, EIP, which I'll explain here in a minute, needs to equal for 1, for 1, for 1, for 1. And this is an example of a fuzz string, like HTTP, a GET request full of A's. We're talking like, you can send 10, 20, 20,000, 30,000. If the program's not written to handle that type of information, it'll crash. And if it crashes in the right way, we get control. So, got to go over a few of the basics. x86 registers. If you see here, EIP is the address in memory. All of these registers point to a location in memory. So EIP points to the next instruction. That's what tells the application what to do next. And this all makes sense when we get the debugger open and we're running through this a little bit. I'll refer back to this. But this is some of the basics. EIP is the next instruction. ESP is the stack pointer. It points to the top of the stack. The rest of it just kind of holds addresses and things for functions in the application. And there's the full list of what each of them means. Not really relevant right at this point. So let's break something. This is a pretty demo intensive. I did have videos because I hate doing live demos, but you can't see them. So I'm going to try to do live demos. So we're going to start with Metasploit.
What was that tweet you sent about?
Yeah. Yeah. Right?
Comma!
Alright, give me just a minute here. Alright, there are some fuzzers built in to Metasploit. I actually don't use Metasploit for doing a lot of my fuzzing. There are a lot of other applications that do it better, but in a pinch, you can use Metasploit. The ones that I prefer are on Windows. Sully is great because it will actually restart the program for you if it crashes. It's got some really, really neat stuff. That's a whole nother hour-long demo on Sully. There's a lot of stuff on YouTube about it if you look it up. And Spike, which is the one that's built into Backtrack, and it's kind of the old reliable. The one that we're going to look at is actually not going to be included in yours, but it's in those files that I had you guys download, which is the TFTP one. This is where you would place it. You guys see that in the hall? Okay, so Pentest, Exploits, Framework 3, Modules, Auxiliary, Fuzzers.
If you go into settings, you can zoom in the font.
Oh yeah?
Go to settings. No. Font. And then enlarge font. Just do it a couple times.
Is that better? One more?
Yeah, it's the colors of the biggest issue.
Yeah. How do you turn that off? Screw it, let's do it this way. Alright, so you've got your, there's the path that you need to place that file, and I'll show you. There it is in the path. This is a very, very, very basic fuzzer. Inside here, it's, I took one of the other fuzzers that was included and just modified it for my purposes because I'm not very good at writing my own code, but I can definitely steal other people's codes and make it fit my needs. Basically, it's, you call the libraries you need, you give it a name, version, description, author. Basically, the important stuff with this is we're going to be fuzzing TFTP. So we set the port to 69. We say that it's UDP, because it is. And then we start the actual fuzzing setup there. Basically, I've set a count. The initial count is it's going to send 100 A's. While it's less than 2,000, send 1,000 A's. Here, this right to here, I pulled that from the RFC. So if you just go out, you can look up TFTP, you can see how the packets have to be structured. So I just pulled that from there. It prints some status information, then it increases the counter by 50 and runs it again. So now, go over to my Windows box. The TFTP server we're fuzzing is TFTPD 32, version 2.21, which was released in October of 2002. So it's been updated. This vulnerability no longer exists, but it's a great example. It's a great first application to fuzz. Again, that's in those files that I put up on the screen earlier. So let's run the fuzzer and show you what it does. Use auxiliary fuzzers, TFTP, simple fuzzer. No options. Well, you can kind of see it. Set our host. We set it to my host that I've got over here, 60. Alright, so you see the application and it's running. When I run the fuzzer, start sending data, it should crash here in just a second. Should crash. Should crash. Live demos. Alright. Make sure all this is working properly. The downside to fuzzing UDP is it won't tell you if it's not connecting. If you fuzz TFTP or TCP, then you get status updates on like if the application is still listening. UDP is just like, hey, I'm going to keep sending this crap on the wire. Yeah, we might be going to the videos because demos are hell. Nice. Alright, video time. As I promise, it breaks. Alright, can you guys see that at all? Barely. Awesome. This sucks. 3, 1, 2, 1. Ha ha ha. 1, 6, 8. Run. Yes! It crashed! Alright, so there we go. We got our crash. Tell this to stop.
Oh yeah, it crashed.
Yeah! Alright, now what we're going to do is, now that we know that it crashes, we want to see how it crashes. I attach it to Immunity Debugger, which is awesome. Ollie Debug is really good, and I like it, but Immunity Debugger is better, in my opinion, because it's got a lot of plugins, and it's Python-based, so if you're into Python and scripting, then it gives you a lot of flexibility. It's really hard to see still. Okay, so over here you can see our registers that I pointed out earlier. The one you're looking for is EIP, this guy right here. We want that value to be 41414141. So let's run the fuzzer again. Wait, oh, we got to start the application. So that's when you attach it to a debugger, it doesn't start. It just loads up into its state there. Okay, now it's running. Now it's listening. Now it's not. It crashed. Go here, kill that. And if you can see, we got our 41414141, which means we have now overwritten EIP. We can control and tell it what to do. So, back to the slides. Awesome. What? Okay, so EIP equals 41, which 41 is hexadecimal for the letter A, so we overrode it with our A's. Now that we control it, we can tell it what to do, but we need to find out where in that series of A's, the 300 to 500 A's we sent, where that 4-byte override occurs. Quickly, any questions? Do you guys understand what just happened there? I sent a bunch of crap to it, it didn't like it, it crashed. Okay. Metasploit has this awesome thing called Pattern Create. It's a standalone app in the Metasploit Tools folder, but it's also built into the framework, so you can throw it right into like a skeleton exploit. What it will do is it creates a easy to determine string of like capital A, lowercase a, 1, capital A, lowercase b, 1. It goes on and on and on and on. That we can then, when we see it overwrite in the IP, we can plug it back into pattern offset, and it will tell us how many bytes it took to get to the EIP overwrite. This is great because the way that I learned to do it before this was basically if you sent 500 A's and it crashed, you would do 100 A's, 100 B's, 100 C's, and you'd figure out where in that chunk it happened. You would have to slowly break it down until you found exactly where it happened. That takes, a 20-minute process that was, and now makes it about a 30-second process if my demo doesn't fail again. So, demo. I should have made so many demos. Okay, so I didn't send you guys all the files to get a complete exploit written. In that, I'll post them on my website, but I gave you the first one, which I'll show you now. Okay, so all this stuff at the beginning here, yeah, that's really easy to read. This all defines the exploit. I, again, didn't write this from scratch. There is an example exploit built into Metasploit that I copied over to my folder and started manipulating to meet my needs. The big thing that I had to change from that was change it from remote TCP to remote UDP. Other than that, I set the space as about 350 characters. X00, the null byte, is a bad character. It doesn't relate to what we're doing right now, but when we add our payload, it will relate. That's where you put, if you know that the program will quit on certain characters coming through, you can put those there, and the encoders will make sure that that character isn't present. 00 is always going to be in there because it's a null byte. It'll end your session. You see there the targets windows. That's where he was talking about in the web interface you saw. You could have multiple targets. This is generic for Windows. I put that 42424242. That is the letter B. So 41's A, 42's B, so on. That's not going to come into play quite yet, but I went ahead and put it there. Then you can see down here, this is the important stuff. If you remember from earlier, it said the RFC, you've got the 0001 starts a TFTP packet, sets the mode. I'm then going to send, using the pattern create, send 300 characters, and then I end it, and then I send it to the wire. So, let me go ahead and try that. Setting the host, 68, 60. You do have to set a payload. But I use a generic debug trap because it doesn't send anything. And I'll restart our service. You just go to debug, restart, and start the process. And exploit. Alright, so it builds the crash, sends the crash. It says no session was created. It's because no session was created. But what is created is this string, 69413569. So that probably means, I'm going to write that down so I don't go back and forth. 69. By the way, when you're doing exploit development, have a pen and paper handy, because you have to write down a lot of crap. Right, Dave?
Right.
All right, so now we go back to this. We'll go to Exploit Framework 3 Tools. All right, so you've got your pattern offset, and you type in that number that we just pulled, 69413569. And it says 256. That means it takes 256 bytes to get to our 4-byte override. That means we have to send 256 A's or whatever, and then after that we put in our 4 bytes for our override for where we want it to go, and then it will jump to there. So, any questions? Seriously, guys? It took me like a month to get this crash. So, yes.
Are you going to put the payload in the first 256? Is that the idea?
No. I'll address that here in a minute. That first 256 is what creates the crash. It's what actually makes the application die.
Right.
And then after that's our 4 bytes.
You're going to set the instruction pointer to
yes, and then
something.
here in a minute, I'll pull it up, I'll show you. Yeah, go ahead and pick something out of the box. We actually have some more space to do with it later on, and it's a little bit easier than that. I'll show you here in just a second. So, I'll show you this one here. This is TFTP 2. Same stuff at the top, same stuff there, but you'll see I commented out the pattern create, and I've got the target.retPackV. This means go up here, get the target's return address, and pack it Little Indian style. That's the way that the processor will look at it. It basically inverses it, puts it backwards. So it's just easier to write it this way. And then you'll see I add, so here it is. This is the crash, A times 256. Here's where I want it to return to. And then 43 is the letter C times 250. So I'm going to throw in 250 C's, see where they end up. See if it's an easier place for me to go, to jump to read the shellcode. And I believe, again, if the demo gods smile upon me. Guys, I don't think you understand. I hate doing live demos, and I made fun of Adrian for doing a live demo, and now my videos that I set up so I wouldn't have to do a live demo don't freaking work. Use exploit Windows Prime TFTP 2. Options. 60. It's running and exploit. Oh, I guess I've got that whole thing I just told you had to do. Generic debug. Now you see why I did videos, because whenever I made the videos and I forgot to do it, I edited that out. Alright, so we got a crash, and if you see EIP equals 42424242, which means what we set up in the target is where we need to go. But there's something else interesting. If you look at ESP, it's really hard to see. Those are all C's. So that means those C's that I injected just a second ago, right after, are being pointed to by ESP. So we want to get to those C's. We're going to have to use a little bit of assembly. What we're going to do is we're going to look for a jump ESP. That's the next instruction we want. Like I said, EIP doesn't contain an instruction, it contains a pointer to an instruction. So we need to find a jump ESP somewhere, and then it will take that and do exactly what it says, and it will jump to the address stored in ESP, which is where our shellcode is going to go. Questions? God, you guys are smart. Smart, idiot. Do what?
The shellcode. C,
right?
Yeah, put shellcode in C's.
Mm-hmm.
That's what I was wondering. How you got the C's in there? You have to put it before it crashes.
Well, no, you'll put, in this example, let me finish it and then we'll see. Let me get to the actual shellcode part.
It counts the question.
All right.
Where's the battery?
So, this is the next one here. I probably should show you how I found it. Let's go back to this. So, overrode it. Now we're going to write a skeleton exploit. We've kind of already got that going right now, but this is an example of what I just did. I forgot to go back to the slides. I just went on with the demo. So sets mode, sends the A's, points to B, sends the C's, ends the packet, or ends the transmission. That's exactly how it was worded. You guys have already seen that. I'll show you that. Woohoo, we're there. Now we control EIP and ESP. The data we want to go to is in ESP. We need to find a jump to ESP, and that will put us right at the beginning of our shellcode. So we're going to use immunity debug in this example. You can use Ollie. They're very, very similar. We're going to use the search functionality. We need to find that jump in either the application or in a Windows library. Now we're really lucky that we're using XP Service Pack 2 here. We'll just use a Windows library because they're loaded in the same place every time. In this example, it's not that way in the rest of the world. And so you guys will find out about that later, but it's not really relevant to this. Then Then we need to test the return by inserting a breakpoint. A breakpoint is something you put in the debugger that as soon as it reaches that address, it pauses execution and allows you to step through step by step. So I can run the program, send my crash. I don't have to step through it processing every A, let it process all that stuff, get to my return address, and I say, hey, when EIP calls this address, which is where our jump ESP will be, stop executing. I want to go through it step by step, make sure it drops me right into the beginning of my shellcode, or do I need to put no ops, meaning do I need to put about 20 no ops because it jumps randomly in the beginning of my shellcode somewhere, and I want it to slide down. So that's why we're going to test the return. Let's break some stuff. Let's pop a box. Woo. All right, so let's see. This is all right. Now that we've got a crash program here, we're going to load up all of the modules that are being executable right now, and I like user 32. So let's go to user 32. We're going to do search for. It's actually readable too. It's very exciting. We're going to type in, you guys can't tell I've done this before, jump ESP, and we found one. And it's at, that's not easy to read, 7E429353. It's an address in memory. So we go back and we plug that into where we had the 42424242, we replace it with that address. So that says, instead of trying to jump to 42424242, which I used as just to make sure I was in the right spot, jump to this jump ESP instruction in user32.dll. So that's what you see here. There's the return address we just found, and this is going to jump. This is going to tell it jump there. Yo.
The address you just found right there, is that basically the same thing as the 4.2 crash point?
Okay, the 4.2, the only reason I use 4.2, it has nothing to do with the crash other than I used it to make sure that I was going to the right place.
You use it as a marker.
It's a marker, exactly, that's what it
The
is.
place that you mark with that 4.2, is that basically the same concept as what this one?
Yeah, this is the instruction. 4.2 was not an instruction, or it was not a place where an instruction existed. It was easy for me to look at it and go, okay, I'm in the right spot. My offset for my crash is correct. It is going to the right place here, and I saw that the rest of my code was being inserted. So, yes, this is basically just an instruction. This just says, hey, I want you to do something now rather than crashing, stopping, and not going anywhere. Because 4.2.4.2.4.2 didn't exist, and so it crashed and said, hey, I can't read memory access, 4.2.4.2.4.2.4.2. So it's something easy for you to see when you're dealing with a crash, and that's just something I do. There's nothing saying you have to do it that way.
If you use any jump instruction with the ESP, you're setting ESP any way you can.
Yeah. In this case, I just use jump ESP from user 32 DLL.
Many of them, it doesn't matter which one you use.
Yeah, well, as long as it gets to ESP, and the most direct route was jump ESP, but there are other instructions that's way more advanced than I'm going to get into in this presentation. But for this example, yes, jump ESP was not only easy to find, it worked, and it got us there with very little fuss. So
using the 4.2.4.2 to just find the spot where you want to input it.
exactly, it has nothing to do with the crash. Past that point, it's just making sure that EIP is being overwritten with the correct, or that I'm in the correct spot to overwrite EIP. We had a guy in the green shirt here and back there both ask questions. Dance monkey.
How does address-based randomization affect this?
I will get to that at the end. It definitely plays a part, but in this and for this example, I didn't want to get into that. That's way more advanced than what we're dealing with here. But it will definitely mess things up.
I was going to ask, that 70 address, that's actually your user 32, that's not in the TFT program, right?
No, that's part of Windows. That's part of and that's why I went to it, because it's
so
prior to address space randomization, it's going to be in the same spot every time.
Right, well, okay, but you're assuming that they're on the same version of Windows.
Exactly. This is heavily dependent on this version. Not only is it dependent on this version, it's dependent on this language pack. It is dependent on many things. This exploit is crap. This thing will not work very many places. But it demonstrates a point. It gets you guys started. It gets you understanding the very basic parts of exploit development. So Yes, let's do that. Go back and restart the program. Actually, I need to put in my jump point. So here we are. Let's restart it. I know 4.2 is not readable. I just got done saying that. All right, so I'm going to jump to that place in memory and set a breakpoint. If all goes well, when the application crashes, we'll stop at that breakpoint.
I need more overweight people to ask questions, by the way. Either that or go out there and see if there's any leftovers.
All right, so make sure it's running over here. Our program is running. We have our breakpoint set. It sends the crash. And you can't see it down here very well, but it says breakpoint at user 32 and our memory address, which means the application has stopped at our memory address. Let's step through that, and there we are. We're at the beginning. I think it should be, yeah. If we go scroll up here, you'll see there's the last instruction it ran, and there's our payload. It dropped us right at the beginning of our Cs, which is awesome because that means we don't have to do a null slide.
Right before that, right next to it, actually says 78. Is that? It's hard to read from here. Is that CC?
Oh, these CCs here?
Yeah.
Yeah, because
Actually, right above that. Like.
Okay. Now, what you're seeing here, you're actually seeing. Hold on a second. Here, let me scroll back up.
Machine code for jump.
No, that is actually not. It is, but that's not why it's there. That is the jump address. That is where we told it to read. So you've got, this is the packet that came in. We sent a bunch of A's, then we sent where we wanted it to go, and then it drops us into our C's. So, and it's actually, I changed it at some point, like when I did this over several days, it went from being the character for C's to this CC, which is a breakpoint. But regardless, what you're seeing here, this 5398427E, if you go back and look, that was the address that we put in back here in Little Indian style. So, yeah. Does that make sense?
Yep.
Okay.
How did you get to the? How did you get to the jump? I know you told it to go into user 32 at that particular spot.
Okay.
And execute that command. How did you tell it to get to user 32?
Okay. Because user 32 resides in that part of memory, I gave it an address. I didn't so much tell it to go into user 32, find this part. I said, go to this address in memory. And that was where user 32 resided, and that's where that command existed.
But you did that by setting the instruction pointer to
I set my return address.
Return address.
The return address, which is what EIP reads,
Okay.
to go to that address, which is what I set in the exploit.
Okay, so the program issued the ret command and grabbed that address from you.
Yeah, it's what I provided right there. That's the address that I provided, and I copied this up here. So here's the address. There's the command that equals jump ESP residing in user 32 DLL.
Okay.
And so
That was the
you
last
saw how I found it. You want me to go over that again, or was that?
No, that's
okay.
okay. That was the last of the A's that you sent in, right?
Yeah, so it's 256 A's. My return address, which is that address
Which jumps you over to the.
that address, which then calls, it jumps to whichever address is in ESP, which is this address right here, which is the beginning of our theoretic shellcode.
And payload will be in
The payload, I'm about to replace all
these.
this with a payload.
ESP is execution stack pointer.
No, it's
What is it?
extended stack pointer.
Extended stack pointer.
Yeah, the E and all that stands for extended. It's when it's for 32-bit addressing.
Okay.
Do you know any,
So
I was going to say, do you know the good debugger for 64-bit applications?
I do not.
iDebug is not.
I have not messed with it.
Is that?
64-bit debugging.
Well, when debugs it.
Yeah, I don't know. I don't do anything with 64-bit stuff. I'm still pretty new at this kind of stuff. So.
You're doing great.
What's up, John?
I was going to say, all your C's, those are blowing out other things on the stack, right?
Yeah.
So there's a good chance you just crash the OS at this point.
No, not the OS, but the application for sure.
The application.
Yeah, the application is going to fail hard here in a second. Now, if I was good at this, I would be able to write an exploit that then fixed all the stack, and the application would keep running, but I'd still get my shell. But I'm not that good at it yet. And that takes a lot of work. So let's go back and see how far off I am in this.
When you threw in the 250, is there a reason a second set of seeds?
I had played with it, and it's actually a pretty limited amount of space there, and 250 worked. I started with 300, and it wouldn't crash quite properly. Crashes are really sensitive to the sizing, so there is some behind the scenes of me playing with this that you just learn as you go through. If you know the program's going to crash, but like in this example, especially dealing with UDP, I don't know where it crashed. The thing is sending it so many packets so fast, I don't know if it crashed at 300, 500, 700, because by the time I am looking at it, and I see 100, 200, 300 days going to it, and I go over to see when the program's crashed and come back, it's at 1,000, 1,100, 1,200. I just have to kind of start making guesses on where it crashed, and I can increase that space. You start with a smaller amount of space, and you can increase it. It stopped crashing after roughly 250 bytes in the shellcode, which is pretty limited, but it was still good enough to do this demonstration with it. So here, now we're going to add a shellcode. This is what actually does something. We have the program, we have it crashing, we have it going to the right place we want it to go to. Now we want to make it do something we want it to do. We want to add a user, we want to pop shell, add an interpreter. In this case, because we're so limited for the space, I'm just going to launch calc.exe. That's usually enough to do a proof of concept, show somebody, hey, you've got a problem in your application. You had TFTP server running, now you have calc running. Something's wrong here, guys. So that's what we're going to add to it this time. Back to that. It's really easy to do. So normally, what I've been doing in the past, and this is actually one of my first exploits I've done in Metasploit. I usually run them in Python. You would have to come back. You use Metasploit a lot. You use the generator for generating the strings, the offset strings. You also use it to generate your payloads. So instead of generating a payload and having to copy and paste it and make sure everything makes it over okay, you replace one line. In this case, we replace this XC times 50 or 250 with payload.encode, and that's it. So then you go into your application, use payload, Windows, exec. So you guys all know what I'm doing here. If you have any questions about what I'm typing in, please stop me. Calc.exe. So there it is. I'm going to restart the application in the debugger. Start it. Jump to that address in memory. Reset my breakpoint. All right, the breakpoint's set. I think I've got everything set here. The God's smiling on me. We will hit our breakpoint. So I don't really want to step through the shellcode line by line. I just want to hit play, and I want to see calc. That's how I know my exploit worked. So there's that, and we can pull it out of the debugger and watch it happen in real time-ish as I have to go back and forth. See, by the time I even go back to it, it's run, the program's crashed, but I have calc. In theory, if it wasn't such a limited space and or through advanced exploitation techniques such as egg hunters, which are really cool, you get a little bit of code that then goes and looks through memory in places where the exploit wouldn't overwrite. Like, let's say we send another command that's not necessarily going to overwrite the buffer, but we'll still place it in memory. If we put a phrase at the beginning, we can take this little 32-byte shellcode. That was probably about 250 bytes of shellcode. We can take 32 bytes, which is ridiculously small, and it'll go through page by page by page of memory looking for that phrase, and when it finds it, it executes everything behind it, which is really, really cool stuff. It's a little bit more advanced than what I'm going to demonstrate here, but Mutz did a great example of it. DEF CON, the NNM exploit. If you go, DEF CON 15, wasn't it? 16. Okay, so Bug to Zero Day is the name of the talk from DEF CON. There's a great video on using an egg hunter and how you can basically make a computer hack itself.
Now, how big are some of the stages that are in Metasploit that are already there for being small payloads that grab the rest of the payload?
It would work normally, but again, this is such a poorly written, just example exploit to get the basic concepts down. It won't work with this. They are usually less than 250 characters or 250 bytes. Now, another exploit that I've worked on only had 60 bytes available for shellcode, which I still haven't figured out how I'm going to work around that. I've talked to Dave about that a little bit, but that's incredibly small. That's a very, very limited amount for shellcode. Like even a basic add user shellcode was like 255 bytes. A reverse shell's up at about 700 or 800 bytes. The cool thing about this app and that fuzzer, if you play with the fuzzer a little bit, there are a lot of vulnerabilities in this app in a lot of different places. So there's one built into Metasploit for this application. It's a little bit better. There's also a lot on the exploit database, which I've got up here in a minute. Go ahead and talk about how the world isn't as happy as it should be. Microsoft kind of started getting pissed at people breaking all their stuff all the time. So they started adding stuff in like address space randomization, which would keep you from doing what we just did there with the address, because every time you reboot Windows, those modules would load in different places. So user 32 is not necessarily going to be there every time. But they kind of half-assed it a little bit, so they only the first 2 bytes are randomized. After that, it's still going to be in the same place. So there is some cool shellcode out there that you can use that'll search for those modules, and you can do some pretty crazy stuff. If you guys are into that, I'll go ahead and pop that real quick. OffSec's Cracking the Perimeter course, the guys that do Backtrack, that class is crazy. It is the hardest thing I've ever done. I had no exploit development experience 4 months ago. I never looked at shellcode. I never looked at assembly. And I enrolled in the course, took it. You will write 3 0 days in the course using manually encoded shellcode. You'll write your own shellcode. You'll do a lot. You'll bypass DEP and ASLR, which are both prevention techniques to keep a lot of these type of tactics from working these days. I can't say enough about it. I know Dave also has taken part of the course, or taken the course, and he recommended it to me. And you agree with what I said? It's one of the craziest classes out there. Mutz is a madman.
Except for all.
Well, yeah. There's the Advanced Windows Exploitation, which I'm hoping to take out of DEF CON this year, or Blackout. But yeah, DEP and ASLR will randomize address spaces. It's enabled in Vista and Server 08 by default, not enabled in XP. And then DEP will prevent you from executing code in non-executable parts of memory. Again, kind of a half-assed attempt. There's a lot of ways around it, but way beyond the scope of this talk. Slides and demos will be on nullthreat.net. I'll try to remember to put everything up there. Guys, if I forget something, put something in the comment. Email me, nullthreat@nullthreat.net. Find me on Twitter, nullthreat. If I forgot something, I forget a lot. Like, I forget I'm here right now. So, tell me what you want. Tell me if you guys need help. I'll help you as much as I can. People that are far smarter than me, Corlan, it's kind of a weird address, but get to his stuff. He has a 9-part series on writing exploits, going from as basic as I did here today, maybe a little bit more basic than what I did here today, all the way up to some of the more advanced techniques. Completely free, completely out there. Goes in more in depth about the registers, what they mean, what they do. DHA at Enclave Forensics, Dave Holzer, SANS instructor, I just got out of his auditing course last week, has a series on YouTube about buffer overflows. See, I'm not big into the reading, learning. I'd much rather watch the moving pictures. So his YouTube channel, he's got a 5 or 6 part series on doing fuzzing, doing buffer overflows, very similar to what I did here, but taking an exploit that's not written for Metasploit and porting it into Metasploit. I used it quite a bit because, like I said, this is my first attempt at bringing stuff into Metasploit. I will definitely be doing it a lot more. It is incredible. And the exploit database. As you guys keep going with this stuff, something that helped me a lot, going in there, finding older exploits, especially for some of the stuff they've got links to the applications that are broken, and you can take the code, run it, you can try putting in different shell code. What I like to do is go in, erase it, make it just a skeleton exploit, and try to go through the whole thing myself. I know this program's vulnerable. I want to fuzz it. I want to find out why it's vulnerable. I want to figure out all the pieces. So that helps me personally. I don't know if that would do it for you guys. Questions? Yes?
With virtual memory addressing and how it takes each stack out, basically it pulls out this bit. When you do overriding, how are you repointing the ESP on a different application sitting in a whole other virtual memory address? So how is it pulling out the ESP from a separate, basically, you're going out of this virtual memory address into this virtual memory address?
One thing
Go ahead. No. You understand it better than I do.
One thing you have to understand with applications is when they create a stack and everything like that, it's a separate portion of allocated memory, and it's always going to be the same memory addresses regardless of whether it's a virtual machine or different types of memory space. So it doesn't make a difference. The addresses will always be the same.
Well, not a virtual machine, but virtual memory address. Where doesn't it take a stack? Isn't that what you're talking about?
Yeah. So it'll take the stack and it'll always be the same memory address.
Oh, so every single okay, so it pulls all of Windows and everything with it to find out the information.
Yep.
It's not just that single application.
No.
Oh, okay.
Well, I mean, it is and it isn't. I mean, like user32.dll is always going to typically be used within an application, or shell32.dll or kernel32.dll.
Yeah, kernel would probably be a better one to use for this.
Yeah, all of them will be used when an application loads. So it'll all be within that application's memory space, even though it's a DLL from a Windows operating system, and they'll always be the same memory.
So if I was trying to hit another application that I know is running on that system, like if I was hitting the FTP and I was trying to move over to another application I know is running, I could move out that virtual memory address into that application?
Sure, yeah. Metasploit does that actually with the migrate process. So it'll actually hook its information in its memory address space into another application's memory address space. So, yeah, actually, absolutely. So, like, for example, like whenever I'm exploiting, and I get an interpreter shell, the first thing I'll do is I'll migrate to like export.exe or something like that, move my memory address space into there. The interpreter prides itself on it never touches the disk. So everything it does is all done in memory. So yeah, absolutely, you move all of your payload information over to another process, and then if you're running on something that's system-based like export.exe or LSASS or stuff like that, you can actually do keystroke logging on the system itself and a bunch of other stuff. So it all depends on what you want to do with it.
Alright, so I got one more demo I'm going to do real fast. Show you this. I haven't ported this into Metasploit yet. This is what one that Martin and I did coming back from the escape from DC. We went to ShmooCon, and I don't know if any of you heard, they got a little bit of snow while we were there. It was like 30-something inches of snow in 48 hours. We all had flights trying to get out of there. Nobody could get out. So my boss John and I decided to drive back. Somehow ended up with Adrian, a very hungover Adrian. And
he picked up his hand, you something to drink. Say no.
Yeah, say no. Otherwise, you have neon green vomit on the interstates. And Martin rode back with us. Martin had gotten this off of the exploit database, right? It was a proof of concept. It was denial of service at the time. Nobody had gotten shell off of this vulnerability.
It was denial of service on Linux Wireshark.
Oh, was it? Okay, so we ported it. I wasn't sure because you had it before I got a hold of it.
Right, I started messing with it on Windows and overrode it.
Yeah, and then I took over a little bit because I just gotten out of that class and had some fun with it. As you can see here, somebody else discovered it, posted it out on the web. As I was talking about earlier, the shell code. Here's the shell code that you would have to bring in, and then it basically builds a packet. I'm not going to get into it deep. It's on exploit database for Wireshark 125.
Yeah, 1.2.5.
Yeah, which I have running over here. And if you guys didn't know, there's a lot of vulnerabilities throughout time in Wireshark because they have all those interpreters that try to make pretty pictures for you so that you can see. And I like that, but it can be vulnerable, and I know we run it a lot at our office. I'll show you guys the danger of running out of date software. Takes it a minute to crash. If it crashes, live demo gods aren't going to screw me again, are they? That would be awesome. Because I just decided to do this. Sweet. Send it again. If it doesn't work the first time, just keep it. There we go, shell. So, we could have put any payload in there. That actually has a lot of room for payload. I think the proof of concept that we put out has calc. You have to do some interesting things to get the other ones to work, but it's a lot of fun because you get to play with the debugger. We had shell working. I've got an interpreter payload working. So if somebody's got an older version of Wireshark out there capturing, I can pull shell in their box on. I think this is universal Windows, isn't it? I think we were pretty much had it tested on every OS, and yeah. So there's that was an interesting one to write. It took a few days.
Did you explain the differences between universal and what's not?
Okay, universal will run on basically any OS, any version.
But why is that?
Yes. I think this one is.
No, reason.
I think this one is universal because it calls libraries out of the application versus out of the OS. So it's not calling user 32. I was able to find all the commands I needed inside of Wireshark. So I used all Wireshark libraries, which weren't protected by any of the safe SEH, and I was able to do all of the commands and everything I needed inside Wireshark libraries. That other one that I did for the demonstration, the TFTP one, would be a lot better if that command appeared in the TFTP or one of the TFTP libraries. It didn't. That's why I had to go outside of the TFTP library. Now, there are a lot of alternative commands I could have used other than jump ESP. But again, it was a simple show you guys this so you can kind of get the idea of what's going on. You can get started. You can start researching. Use those resources. Core LAN stuff is amazing.
Now, could you capture that traffic and then open the capture file locally with Wireshark and have it crash out that way?
I haven't tried that, but that's an excellent idea. I'm going to try that when I go sit down. I'm going to do that. So, what's up?
How do other OSs handle address randomization?
Like Linux?
Like Linux or Mac OS 10? Or do they do anything at all?
Linux does. So does OS X. I have not done any OS X stuff. I just got that. Is it good? The OS X or the Mac OS 10 Hackers Handbook or whatever? Yeah. Dino DiZovi and Charlie Miller. I just got a hold of that, so I'm just going to start. I've never played with it. And my Linux exploit development experience. That's one thing that's not covered a whole lot in that Cracking the Perimeter class. It's very Windows heavy because that's mostly what you're seeing out there. So.
How hard does it make it for people who want to fuzz applications if the application is encrypted, hacked, virtualized?
I haven't done a lot of anything there's so many just crappy Windows apps on download.com that I'm going crazy on those. I just fuzz all that stuff just to play because I'm still getting to the beginning. I try not to make it too complicated on myself because, again, I'm still very much in the learning phase for this stuff. So it's, I imagine it would pose some trouble.
When you're fuzzing,
it's just whatever the application's willing to accept. You're not trying to bypass any protection. You're just taking what the application's waiting for, what it's listening for, what it's willing to accept, and you're sending it stuff it doesn't expect, like special characters. That's one thing that will crash a lot more applications than you would be comfortable knowing. Way too much information. In this example, was just a bunch of A's that did it. A bunch of semicolons will crash something else. Maybe the application's built to handle 250 A's, but 500 semicolons, and so you get more space later on. Like I said, if you're doing Windows stuff, Solid is awesome because it will, and even some of the stuff it'll do with virtual machines where if you're fuzzing an OS, I think it's basically what it is. So if you're fuzzing Windows, and it notices that Windows has crashed, it will contact VMware control and tell it to reboot the machine. And so it'll reboot the VM, not send any more data until that VM has come back up, and then start sending fuzzing data where it was. It's got a neat web interface where you can see all the overwrites if you see in the IP at 414141. There's plugins for WinDebug, Bang exploitable by Windows that will tell you how likely you are to get a working exploit, because not every crash leads to an exploit. You will get, if you start fuzzing apps, you'll get a lot of crashes, and maybe 1 to 2 of hundreds will result in a place for you to get an exploit. So, but fuzzing, there are a lot of great books I didn't mention. Fuzzing, brute force, vulnerability discovery. Do what? Yeah, okay, so it's got a big bear on the front of it. Again, I told you I'm not much into book learning, but I do have some. Shellcoder's Handbook, also fantastic book, and Hacking the Art of Exploitation 2. All three of those, if for no other reason to have laying around, if you're getting into this stuff, if you want to do this kind of stuff, you need to have them laying around to refer to when you get into something crazy. Also, pound Metasploit on IRC, pound OffSec, IRC. Backtrack is probably not going to be the thing. Martin, would you yell at people if they came into Backtrack Linux and started talking about fuzzing? You probably would, wouldn't you?
As long as you put backtrack in the sentence somewhere.
Okay. Yeah, so don't come in and start talking about, I'm in Windows, I'm playing with Sully, help me. Because they probably won't be too cool about that in there.
Backtrack, and that'll be all right.
Yeah.
You say it 4 times, you're safe.
So, yeah, just backtrack. How do I do this?
Backtrack.
You see backtrack 3 times in the mirror, it summons mutts.
Yeah. Any other questions? Did you guys kind of get that? I mean, it didn't go too far over y'all's heads because I was really afraid it was either going to be way too dumb or I was going to overthink it and put too much in there. So, excellent. All right, here you go, guys.